This presentation is about gears, pulleys, drives, and sprockets, and the gear ratios that we're going to see when we use different size gears, pulleys, drives, and sprockets. Why would we do this? Why would you do this? What are you thinking? Well, obviously, we can change the speed of rotation by changing the sizes of our gears, pulleys, and sprockets. We can also change the direction of rotation. Maybe we have an axle spinning one way and we need to spin a different way. Not only clockwise versus counterclockwise, but actually different angles also could be achieved. We can change the amount of torque available to do work. If you have a car engine, you're going to need some gears to lower down that gear ratio so you can get the car moving. And then as you move, you'll want the gear ratio to change, and the torque available to the rear wheels will change as the speed goes the opposite direction. Torque will become less and less available, speed will become more and more available. All right, so we'll take a look at that. These pictures here, we have a gear ratio in a set of gears in an engine. We have some belts. These pulleys and belts are in a lawnmower that it'll spin the blades. You can see all the dirty stuff on the wheels there. And then we have a classic bike, motorcycle that has a large chain and sprocket system to drive the rear wheels. So gear train. Let's talk about gears first. We're going to transmit our motion and our torque through interlocking teeth. So these gears have teeth either machined or cut into them, and these teeth, or also called cogs, interlock with another gear. So of course the gears have to be matched. You can't just have any old gear drive any other old gear. They have to have the same sort of size, same shape. They have to have faces and flanks that match to each other, and also pitch. Just like what we talked about with screws, gears also have pitch. If we measure from one face to the next face, you have your pitch. When we talk about these, we're going to have the driven gear and the driver gear. So one gear is the one that we're going to put all our motion into, and then we're going to have another gear that the motion comes out of. And there could be a whole series of gears. The driver gear is going to be getting the energy. The driven gear, whether it's the second one or the last one, is going to be getting that energy. So here we have examples of gears that are mating and easily interlocking with each other, and you can see the faces and the facets contacting. In the second one, you see we have a third gear that is in between the first and the last. This is called the idler gear. And let's take a look at the motion. If you notice, the motion of this gear, when it's clockwise, the motion of this gear is counterclockwise. There's no other way for it to go, and that's always going to be the case. When you go from one gear to the next, the direction of motion will be opposite. So why would you put this little idler here? Well, this idler can serve several different purposes. One, it could be a spacer. Maybe this first axle, this axle here, needs to be a certain distance away from this axle here, maybe to make room for a motor, or to make room for tires, but you need to transfer energy still. Well, that idler can do that for you. Also, that idler can change the direction back again. So if our motor here is spinning a certain direction and we need our wheel to turn the same direction, then we could put an idler in between. Or let's say that this and this these two axles represent wheels on the same side of a vehicle. Well, you want them to spin the same direction. You can't have spinning opposite directions like this. So the idler can do that for you. So this idler does not change the gear ratio, as we're going to see in a little bit. We won't have any change in gear ratio because of that. When we look at sizes, and you can see here we have this blue gear is larger than this red gear. The larger gear is always going to be moving slower than the smaller gear. And of course, we can see that if we recognize that this gear is going to have to go around a lot more times, all right, than this gear does. If it's a ratio of, let's say, 2 to 1, then this little gear is going to have to go around twice for every one time this bigger gear goes around. Now, you notice these two gears, the blue one and the greenish yellow one here, they're on the same axle. They're attached to each other. So every time the blue one goes around once, the green or the greenish yellow one also goes around once. So they have no gear ratio between them. Or you could say they have a 1-to-1 gear ratio between them. So let's talk about the variables that we have. N is the number of teeth. This is often the easiest way on a gear to figure out what your gear ratio is by counting the number of teeth. So that's an important value. Diameter, that's also another value. You can measure from one end to the other. And because the teeth are the same exact shape on both gears, that's another way you can measure from one side to the other like that. That little symbol that looks like a W, all right, that is the omega symbol. All right, one of those Greek letters. And it stands for angular velocity. How fast are these spinning? All right, we're going to be measuring that in RPMs, revolutions per minute. How many times does this revolve every time a minute goes by? And typically, if you look on a tachometer on a car, it's going to be measuring how fast that engine is revolving every minute that goes by. So it's measured in RPMs. And then looks kind of like a T, but it's the tau symbol, T-A-U. And that stands for torque. And so it's just like a little stylized T. And torque is that ability to spin things. So you can see, of course, that's going to be very important with gear ratios because we're spinning them. Now, let's take a look at here in our situation. The N has 6 teeth. It has a diameter of 2 inches. It has an RPM or angular velocity, of 40 RPMs, 40 times a minute that little gear revolves. And it's got a torque of 40 foot-pounds. In other words, something is providing 40 foot-pounds of torque on that red gear. Well, let's look at our output gear. Our output gear is twice as many teeth. Doesn't seem fair, does it? Some people get a lot, some people get a little. Its diameter is 4 inches, twice as big. Its RPM, half as much. And its torque in foot-pounds is also twice as much. So if we drive that little red gear at 40 foot-pounds, we can get 80 foot-pounds of spinning ability out of torque out of that blue gear, out of that blue 12-tooth gear. So everything doubles, half, double. All right, notice that? That's going to be important when we make our calculations. We're going to see that the out of the teeth and the out of the diameter and the out of the torque, they all double. But whereas the angular velocity, no, it's half. All right, and we understand why from my description on the previous slide that this is going to spin slower. So it's going to have half as much RPM, but double the torque. And so if you're the designer and the engineer, these are important factors that you're going to consider when you choose your gear ratios. So let's take a look at our equations. You knew we were going to have equations, right? Well, you should have. Gear ratio, that's the key thing. And when we talked about simple machines, we were very concerned with mechanical advantage. There's a lot of parallels between gear ratio and mechanical advantage, and we're going to talk about those as we progress through this slideshow. Boom! There we go. So gear ratio, I have a gear ratio over 1, it could just be GR, is equal to the number of teeth on the output gear divided by the number of teeth on the input gear. Or it could be the diameter of the output gear divided by the diameter of the input gear. Or it could be the angular velocity of the input gear divided by the angular velocity of the output gear. Or we could also find gear ratio. Yeah, a fourth way? Yes, a fourth way. It's very exciting, isn't it? The torque of the output gear divided by the torque of the input gear. All right, you should write this equation down in your engineering notebook so that you have it available for you. So notice, though, that the angular velocity of the input gear is on top. Let's see here. Out, out, in, out. This is the oddball, all right? This, in all of our equations, this one's the oddball. It's got in on top and out on the bottom. Why is that? Well, we just saw that when you put that little gear up against that big gear, the number of teeth doubled in this situation, and the diameter doubled, but the angular velocity was in half, all right? But also the torque doubled. So it makes sense that this equation would be the other way around. In our case, let's plug in some numbers and find out what happens. So we said that we had an output of 12 and an input of 6. So we have 12 over 6. We don't know our gear ratio yet, but I think it's going to become apparent real quickly. We have an output of 4, an input of 2 inches in our diameters. As far as angular velocity, you remember that that was 40 RPMs was the input, but the output was 20 RPMs. RPMs cancel, we get a unitless number. And what about the torque? Oh, mystery. 80 foot-pounds of torque divided by 40 foot-pounds of torque. Remember, we were putting 40 foot-pounds of torque into this system and getting 80 foot-pounds of torque out. So that's great. But we're not manufacturing energy here. We're not manufacturing work. There was a price we paid. We did get a lot more torque, twice the torque, but we got half the speed. Notice, torque and speed, there's a trade-off there. All right, if you hadn't noticed, you need to notice. If you did notice, good for you. And again, of course, those units cancel, and we're left with a unitless number of 2 to 1. So this is an easy way to figure out gear ratio because you have all these different methods. Like I said before, if you're the designer, you're probably going to be looking at teeth and diameter. And then by knowing the teeth and the diameter, you'll know more information about what's going to happen to the speed and the torque. What's the gear ratio between A and B? Why don't you go ahead and pause the video, do the calculations, use the number of teeth to figure out the gear ratio. So you should have divided the number of teeth on the output gear by the number of teeth on the input gear, or 12 divided by 20. That's a 0.6 to 1 gear ratio. All right, what about from B to C? Give that a try. You got the 12-tooth gear and you got the 5-tooth gear. Pause the video, do the calculation. Very good. Let's take a look. We have the number of teeth on the output gear at 5, and the number of teeth on the input gear is 12. That gives us a 0.42 to 1 gear ratio. Let's stop for a second and talk. What does this mean? I mean, it was kind of easier to think about it when it was 2 to 1. That little red gear was spinning twice as fast as that bigger gear. So what about this? Well, this gear here is larger, and it's spinning a smaller one. So the smaller one is going to be spinning the fastest. And that means that every one time this smaller gear goes around, this gear only goes around 0.6 of its entire rotation, just a little over halfway. So when this big gear goes a little over halfway, this 12-tooth gear has already gone all the way around once. We know this little red gear is going to spin faster than this 12-tooth gear. So what about that? Well, every time this 12-tooth gear spins around 0.42 times, this little red gear will have spun once. We could look at it the opposite. If we took the inverse of this, then you'd know how many times this little red gear spun around for every one time this 12-tooth gear spun around. Next question. What about the gear ratio from C to D? We got a 5-tooth gear driving a 20-tooth gear. Let's pause the video, do the calculation, and what do you get? You should have divided 20 by 5 and gotten a 4 to 1. Whew, much different, right? Because now we have, instead of having bigger gears driving smaller gears, now we have a little teeny gear, 5-tooth, driving this 20-tooth. And you can see, of course, there's a 4 to 1 ratio. This is 4 times bigger than 5. So every one time this goes around, this is only going to go around a fourth. Or every time that our driven gear goes around once, our driving gear, our input gear, has to go around 4 times. So what do we get when we put all of this together, and how? How would we put all of this together? How would we figure out what the overall ratio is for this entire gear train? Well, that's what we want to know. We're going to multiply all of them together. Just like a mechanical advantage, when you multiplied all of the mechanical advantages together in a compound machine to get the overall mechanical advantage, you do the same thing here with gear ratios. You multiply all the gear ratios together to get a total. And so we have 0.6 times 0.42 times 4, and we get a grand total of 1. Not very exciting, but if we had looked at this closely and you remembered what I said in an earlier slide, I told you that idler gears don't affect the overall gear ratio. Well, we have a 20-tooth gear here and a 20-tooth gear here. I think we can all see that 20 divided by 20 is the same as 1 divided by 1. So those two idler gears didn't actually really do anything. They probably robbed us of a little bit of energy. There's a little bit of friction, a little bit of noise, and so forth. But for some reason, in this gear train, they were necessary. Maybe it was to space these two out, get them farther away from each other. Maybe they're driving other things. Sometimes you do that. Sometimes this gear or this little gear will drive some other component so that they're necessary. But the overall gear ratio from here to here is the same. Another option would be for something like this is you could mount a motor on this gear and another motor on this gear. And then those two motors could spin exactly the same speed and they'll be attached to exactly the same gear size. That'll work out really well. So both those, the blue one and the yellow one, would be spinning at exactly the same speed. And then maybe these two could be your output gears. All right? There's all kinds of different options you can have with gears and gear ratios. If A and D were directly connected to each other, what would be the resulting gear ratio? Well, we've already talked about that. It would be 1 to 1, right? 20 divided by 20. So what would be the total gear ratio if the last gear had 40 teeth instead of 20? So go ahead and pause the video and do the calculation. All right, that calculation should have produced a result of 2 to 1. We have the 0.6 times 0.42 times 8 to 1, right? 40 divided by 5 would give you an 8 to 1 gear ratio. Or if you had an input of 20 teeth and an output of 40 teeth, you'd have a gear ratio of 2 to 1. And that's because we ignored those inner two. Now, that's only in a drivetrain like this. There are no compound gears here. So it's a little bit different if you have a compound gear. And we'll be talking about that coming up shortly. Let's talk about gear ratios versus compound machines. So in simple machines, if we rearrange the equation for mechanical advantage, remember mechanical advantage was equal to the force out divided by the force in. So if we just rearrange the equation and move force into the other side, we end up with this equation here. Force out is equal to the mechanical advantage times the amount of force we put into our simple machine. We can do the same thing with torque. I mean, you can look at this torque equation, and it's a very, very similar equation. The amount of torque we get out of our system is equal to the gear ratio times the torque in. Now, when we saw this equation earlier, it was torque out was divided by torque in. So let's go ahead and we'll change that. Make that look more similar to what you were used to. So if you cancel those, boom, gear ratio is equal to torque out over torque in, right? Just like you saw it before. So we did this to show you the similarities between the two. Now, what about the overall mechanical advantage? Well, like I said in the previous slide, the overall mechanical advantage was the mechanical advantage of every single individual simple machine all multiplied together. And we get the same thing, the same results when we multiply all the gear ratios together, or at least a similar result. You take gear ratio 1 times gear ratio 2 times every single gear ratio in between to the final gear ratio, and you get the total gear ratio, just like we did in the previous slide. Let's take a look at compound machine. Here we have both simple machines and a gear ratio in between. So we have three mechanisms. So here we have a moment arm of 4 inches long connected to an axle. And of course that axle is then connected to a gear that drives a smaller gear. That smaller gear has only 24 tooth as opposed to this larger gear of 60 teeth. And then this smaller gear, this 24 tooth gear, it has an axle going through it. And that axle is connected to another moment arm. That moment arm is 4 inches long. So the moment arm, axle, gear ratio, axle, moment arm. We have three different mechanisms here, all working together. Our effort force is going to be applied to the end of this moment arm, making this 60-tooth gear spin around in a clockwise fashion. If we push up on this bar, everything here is going to spin around this way. Well, what happens to the blue gear? If this gear spins around clockwise, then this blue 24th tooth gear must spin, that's right, counterclockwise. They have to spin opposite directions. Well, if it's spinning counterclockwise, then that means this moment arm is also spinning counterclockwise, and it will be moving upward, and that's our resistance force. That's the force that we want to apply. So we want to push here and get a push here as the output. What's the mechanical advantage of our moment arm? Well, we have a 4-inch long moment arm and a gear that's 1.5 inches. So the mechanical advantage is 4 divided by 1.5, or 2.67. So this is very important to look at. There might be a mechanical system like this that you put together for your simple machine. When you attach an arm to a gear like this, the gears that we have in the lab do have screw holes, and they're a locking mechanism that you can use to hold this together. So you're going to get a gear ratio of 2.67. So you're going to have a mechanical advantage. It's going to be, this arm is going to make it easier to spin that gear. Take less force to put in than what you're going to get out. What about our next mechanism? Well, our next mechanism is the gear ratio. So we have a gear train from the 60 tooth to the 24 tooth. So this larger 60 tooth gear is not going to have to spin as much as the blue, or I could say it the other way around. This blue one is going to spin around a lot more than the blue one, right? So we have 24 teeth divided by 60 teeth. So we only have a gear ratio of 0.4. So the amount of torque we put in, we're going to get less torque out of it, aren't we? Very good. So let's look at our third mechanism. Our third mechanism is the last wheel and axle. And this wheel and axle, we have a 0.6 inch gear divided by a 4-inch long arm. So we only have a mechanical advantage of 0.15. So you're going to have to put a lot more force into this than you're going to get out from this system, this third mechanism. Very interesting. So let's take them all together. The two mechanical advantages we can multiply together, and that gives us a total mechanical advantage of 0.4. So we have this really large mechanical advantage initially, but our final mechanical advantage, not so big. So overall, the amount of force you put into this is going to have to be greater than the amount of force you're going to get out. What about our gear ratio? Well, that was 0.4. So you're going to have to put a lot more torque into this than you're going to get out. But what are you going to get? You're going to get speed. So when this arm goes clockwise, this arm's going to go counterclockwise much faster. But because of the decrease in mechanical advantage, it's going to take a greater force that you put in here than what you're going to get out here. So let's take a look at a compound gear train. We've got a set of gears down here, the blue one, a yellow one, a green one, and a red one. And we're going to put them together in a more complicated drivetrain because we're going to have compound gears. So let's see what happens. Our driver is going to be the green one. All right, ooh, we look at it spin clockwise. So we're going to add to that this yellow gear. The green one is going to drive the yellow one. So now it's spinning counterclockwise, the opposite direction. As you can see, the green one is spinning faster because it's the smaller one. The yellow one's spinning slower. Next, we're going to add the blue one. And it's going to sit on the same axle as the yellow gear. And you notice that they're spinning at 1-to-1 ratio because they're attached to each other. They have no choice. So they're both spinning counterclockwise. The yellow one is spinning slower than the green one, and the blue one is also spinning slower because it's being driven by the yellow one. If that blue one was attached to the green one, it would also be spinning slower, but not as slow as that yellow one because it's a lot closer in size to the green one. But because it's attached to the yellow one, it has to spin the same speed as the yellow one. All right, we've got one more gear left, that red one, and we're going to add that as our output. And we're going to put the output on the blue one. Now we have the blue gear driving the red gear. So we have a gear ratio between the green and the yellow. We have a 1-to-1 gear ratio between the yellow and the blue. And then we have a separate gear ratio between the blue and the red. So let's add some numbers to those gears. Stop them. And we have some actual numbers of teeth. So we can actually calculate the gear ratios. And I know that's what you really wanted. You don't want to see spinning gears. You want to do the math. What's the gear ratio between A and B? Go ahead and write that down and calculate it as you pause the video. Well, the output gear is 4 times bigger than the input gear, so we're going to get a 4-to-1 gear ratio. Very good. What's the gear ratio between C and D? We already know B and C. We don't need to do that one. That one's 1-to-1. So what about from C to D? Pause the video, do the calculation. All right, very good. Well, our output gear is 50 teeth compared to an input gear of only 20 teeth. So we're going to have 50 divided by 20, and we get 2.5. So what is the gear ratio of the entire gear train? Pause the video, the calculation. So we had a 4-to-1 gear ratio from A to B and a 2.5 gear ratio from C to D. So we needed to multiply those together to get the overall gear ratio. So we ended up with the overall gear ratio of 10-to-1. So that little gear was spinning 10 times every one time that big gear. Let's take a look at our previous slide. Yeah, it looks like it. That little green gear is just whizzing along at 10 times the RPM of that big red output gear. Excellent. Let's move on to the pulley and belt system. Okay, pulleys are very, very useful. I showed you a picture of a pulley system and a lawnmower engine in the second slide of this presentation. Pulleys are wheels that usually have a groove. In that groove, a V-belt will fit into it. Both these pulleys have grooves in them, and there's a belt that is going all the way around inside that groove and then around to the next to pulley, from pulley to pulley. You can have tooth pulley systems, but in this video, we're going to just talk about smooth, grooved pulleys. What about our equations? Well, these look very familiar. We can't count teeth anymore. There are no teeth to count. We can look at the diameter of the output versus the input. We can look at the speed, the angular velocity of our input divided by our output, or we can look at the torque of the output versus the torque of the input. So we're not going to call this our gear ratio because these aren't gears. They're belts and pulleys, but they do have a ratio. And so let's calculate what the ratio would be of this pulley system. So we have a 6-inch output versus a 2-inch input. So 6/2, or we can look at the RPMs. The RPMs of the input were 30 RPMs, whereas the output was only 10 RPMs, 1/3 the speed. Or we can look at the torque. For the torque, we had a 55 foot-pound output versus an 18 1/3 foot-pound input. So we're getting a lot of work out of this. So we're getting a real benefit with the torque aspect, but not a benefit in the speed aspect. All right, we're going to have to spin at 30 RPMs and only get 10 RPMs out of it, but we're going to put in only 18 1/3 foot-pounds, and we're going to get 55 foot-pounds as our output. So we're sacrificing speed and we're gaining torque. Excellent. So you can see there that that ratio is a 3-to-1. Right? When you divide the 6 by the 2 or the 30 by the 10, or the 55 by the 18 and a third. Very good. So those are pulleys. What about sprockets? Well, you should be very familiar with sprockets and chains. You see these on bicycles, but not just on bicycles, a lot of systems. Inside motors, for example, the timing that's controlled between the crankshaft and the camshaft. The crankshaft is what drives the pistons up and down inside a motor. The camshaft is what opens and shuts the valves in your motor. And it's very important that the timing be controlled very, very precisely. When those pistons are going up and down, you need those valves to open and shut at just the right time. For those of you not familiar with motors, one valve has to open to allow a fuel-air mixture into the cylinder, and then it has to close at just the right time to get compression, to get combustion, to get power out of that motor. But then when you're done with all those fumes, you need to exhaust them out the back. So you need the exhaust valve to open, and it has to open at just the right time as the cylinder is coming up and pushing all that material out. So this happens in some motors that don't have valves. They're two-stroke. So it happens every 2 times that the motor turns around. In a typical car engine, which are called 4-stroke engines, this happens every 4 strokes. So every 4 strokes in one cylinder, you're going to have intake, you're going to have, so that's the downstroke, you're going to have compression on the upstroke, and then you're going to have combustion, and that's going to push the cylinder back down. That's the 3rd stroke. And then on the final upstroke, you're going to have exhaust. So those valves have to open at just the right time, or you got no power, or you have backfiring through the carburetor, or you have exhaust is full of gas and air instead of the exhaust from the combustion. Well, in most engines, this is controlled by a sprocket and chain system, like this. And of course, a sprocket is going to have teeth. There's going to be spacing between those teeth, and that spacing is called the pitch, just like we had with screws. And the chain is going to fit nicely on there. And not every sprocket works with every other sprocket. There's one typical pitch that's used for bicycles, and there's other pitches that are used in machinery and other mechanisms. So let's take a look at what we have here. We can't count teeth, right? No, we can. We can count the teeth because we're back to having teeth. We have an output number of teeth, an input number of teeth, and we can divide. Or we can look at diameters. We can measure the diameter of our sprocket on the output side and the diameter of our sprocket on the input side. Or, remember, we flip this and we look at the speed of the input and divide that by the speed of the output, our angular velocity. Or we take the torque of the output and divide it by the torque of the input. So again, you're seeing that switch here between speed and torque, that when one goes down, the other goes up, and vice versa. If you count the teeth, we have a 22:11 ratio. If you look at the diameters, we have a 3-inch output versus a 1.5-inch input. So let's look at the angular velocity. Our input sprocket is spinning at 90 RPM, whereas our output sprocket is only 45 RPM. 90 divided by 45, that's going to give us our ratio. Or, cancel out, of course, the units, we can divide 120 foot-pounds of torque that we're getting on that output sprocket versus the only 60 foot-pounds of torque that we're putting into our input sprocket. So this, if we want to put this in bicycle terms, this would be like when you're at a very low gear and you're spinning fast, all right? Your pedals are spinning really fast, your legs are pumping up and down really quick, but you're not going very fast. Why would you do that? Well, it's very useful for going up a hill or maybe just getting started. It gets the bike moving, and then you can start switching into higher gears. You're spinning really, really fast, right? You're spinning really, really fast, but the output is not spinning nearly as fast. But you're only putting in 60 foot-pounds of torque, and you're getting out 120 foot-pounds of torque. Again, I want to point out how these swap. When you go really fast, you can get a lot of torque out. Or switch it. If you made this the input gear you made this the output gear, then you could put a large amount of torque and get out a small amount of torque, but you could put in a small amount of speed and get out a lot of speed. And of course, the units for those torque cancel out. So let's compare. So the method of transmitting force between pulleys and sprocket. So with pulleys, we use a rubberized or flexible belt. With sprockets, we use a chain. Advantages of a pulley system: they're much quieter. They don't need lubrication in the same way, to the same degree that a chain and sprocket does, and they usually are cheaper. Sprockets, they're not going to slip as much as a pulley system. You can put a lot more load on them without having to worry about slippage. And you're going to get a lot more strength. In a system under very, very heavy loads, you're going to get a much more reliability out of a chain and sprocket. Disadvantages: the pulley can slip. Now you can switch to a toothed pulley, and that's kind of a compromise between these two. But if we go back to chain and sprocket, the costs are higher. It does need more lubrication. They can be noisy, and there's also a weight disadvantage too. Sprocket systems are heavier than pulley systems. All right, thank you very much for watching the video.